Hi everybody and welcome to the next chapter. So in this chapter on differential calculus, we will cover a number of topics. So we'll talk about tangent lines, which is a topic that we've already covered in coordinate geometry, but we'll use that to make the link with the notion of a derivative, which we'll define rigorously later on. And then we'll talk a little bit about the relation between functions being differentiable and continuous. And we'll finish off with a number of rules of thumb that you can use to compute derivatives of pretty much all of the functions that we've covered so far. So polynomials, exponentials and logarithms, trigonometric functions, and so on. And then last but not least, we'll have these two rules, which are quite general, which will allow you to differentiate combinations of already known functions. So in order to set the stage, let's have a look at the example that I already mentioned of the tangent line. So a few lessons ago, we looked at the parabola y is equal to x squared. And we computed the tangent line at the point P11. And that tangent line looks a bit like this. So it touches the curve, but it doesn't intersect it in 2 points. So it just touches the point of the curve. And the way that we computed that tangent line is we used a limit. So we said the tangent line to y is equal to x squared at the point P11 has slope m given by the following limit. And how did we compute that limit? Well, we took another point Q and then we let Q approach P. So Q has coordinates x, x squared. And so the limit becomes the difference of the y values, so x squared minus 1, divided by the difference of the x values, x minus 1, and then x goes to 0. So in the denominator, or in the numerator rather, we have delta y, the difference of the y coordinates, and in the denominator we have delta x, the difference of the x coordinates. And then we can simplify this expression. We can calculate the limit to give limit of x plus 1. And finally, we find that the slope is equal to 2. So now there's nothing preventing us from doing the same calculation for other functions. So let's see how that works. Let's take the graph of an arbitrary function y equal to f of x. And let's take a point P here with coordinates a, f of a. And again, we want to compute the tangent line to that point, so probably that line is going to look a little bit like this. So in this case, the tangent line has slope given by the following expression. So we do exactly the same thing. We take the limit, and now we take another point Q with coordinates x, f of x. So we take the difference of the y values, f of x minus f of a, divided by the difference of the x values, x minus a, and we let x go to a. So again, this here is delta y, the difference of the y values, and this is delta x, the difference of the x values. And so here, just to be precise, tangent line to y equal to f of x at x equal to a. So this is a very important expression, which will give the name of the derivative of a function, but we see it first here as a way to compute slopes of tangent lines. So let's look at a couple of examples before we move on with the concept of derivative. So for the first example, we'll take the tangent line to y equal to x to the power 4 at the point P11. So in order to compute the slope, we use the formula. So it's the limit of x going to 1 of f of x, that's x to the power 4, minus f of a, that's 1 to the power 4, or just 1, and then divided by x minus a, so x minus 1. And now we have that fraction here, which we can simplify. We can actually compute exactly what that is, and we'll see a way of doing that later on. If you don't know how to do it, just take this result as given. X cubed plus x squared plus x plus 1. And so the limit becomes 1 plus 1 plus 1 plus 1. And that's equal to 4. So now that you know the slope, you can also figure out what the intercept is. And you should get that the tangent line is given by y equal to 4x minus 3. For the second example now, we'll take y equal to the cube root of x, and we'll compute the tangent line at the point P with coordinates 0, 0. So now the slope is x going to 0 of cube root of x minus 0, or minus cube root of 0 if you want to be precise, divided by x minus 0. And that simplifies a little bit to cube root of x divided by x. And then if you remember the rules of the powers, you can write this as 1 over x to the power 2/3. So here, if you let x get smaller and smaller, what you will find is that 1 over x becomes larger and larger. So this limit becomes plus infinity. And so what does that mean? Well, this means that the slope does not exist. In other words, the tangent line is vertical. And you can also see that if you look at the graph of the function, the function y equal to cube root of x looks a bit like this. It becomes vertical at the origin and then continues like this. And in particular, we have that the tangent line at the origin, my drawing is not exactly right, but the tangent line is vertical. And then the third example, let's try to calculate the tangent line to ln of x, the natural logarithm, at p equal to 1, 0. So again, we have for the slope that it's the limit of x going to 1 of ln x minus ln of 1 divided by x minus 1. There's a very small simplification, of course. Ln of 1 is equal to 0. But in general, if you look at this limit, x going to 1 of ln x, x minus 1, this is not something that we can compute right now. So it's not at all clear what this is, and in fact, we'll have to do a bit of work to figure that out. So the whole goal of the next set of videos is to find rules that will allow you to calculate limits like these and derivatives like that. So I've already said that this expression for the slope is very important and that it has its own name, it's derivative, so let's make that more formal. So the derivative of a function is given by that limit that I already mentioned. So derivative of a function f of x at x equal to a is given by the limit of x going to a of f of x minus f of a divided by x minus a. And now, since it's an important thing, it has its own notation. We denote the derivative by f prime of a. So this here is referred to as f prime. And there's a slightly different way of computing the same thing, also as a limit. So in order to figure that out, we'll put a new quantity h equal to x minus a. So then what you have is that this becomes the limit of f of a plus h minus f of a. And then x minus a is h, so h here, and then the limit of h going to 0. So this is also equal to the limit, of course, to the derivative, and sometimes this is easier to compute. And a little bit of terminology. If f prime of a exists, and here in both cases it's important that the limit should exist. But if the limit exists, then we say that f of x is differentiable at x equal to a. So differentiable is just another word for saying the derivative exists. So let's do a couple of examples. So for the first, let's compute the derivative of f of x equal to 3x squared plus 7x minus 5 at x equal to 1. So it's f prime of 1. And we'll use the second form, so it's the limit of h going to 0 of 3 times 1 plus h squared plus 7 times 1 plus h minus 5 minus the value of the function, so 3 times 1 squared plus 7 times 1 minus 5, and all of that divided by h. So now we work out what the denominator and the numerator are. So we get 3 plus 3h squared plus 6h, and then plus 7 plus 7h minus 5, and then here minus 3 minus 7 plus 5, and all of that divided by h. So cancellations, 3 minus 3, 7 minus 7, and minus 5 plus 5 all cancel out, and we're left with limit h going to 0 of 1 over h, 3 times h squared plus 13 times h. And so now we can divide out the h to get 3h plus 13, and so the limit becomes 13. And we get that our derivative is equal to 13. This is a bit involved. In the next few videos, you will see some rules which will make computing the derivative of a polynomial a one-step process. So keep that in mind for when we see the next few rules. For the second example, we'll take the derivative of y equal to the absolute value of x at x equal to a, and we won't specify what a is, so it's just an arbitrary number. So there's going to be 3 cases to consider. First of all, a bigger than 0. So in that case, f prime of a is the limit h going to 0 of absolute value a plus h minus absolute value of a divided by h. Now, some simplifications that we can make. So we have a positive, and therefore absolute value of a is equal to just a. But also what we have is that for h small enough, a plus h is also positive, and therefore absolute value of a plus h is also just a plus h. And you might wonder why, or can we be sure that h is small enough? Well, yes, because we're going to take the limit h going to 0, so h is becoming smaller and smaller. So with that, the limit becomes a plus h minus a divided by h, and so you get limit of h going to 0 of h divided by h, and that is just plus 1. So now for the second case, a negative, we can do pretty much the same thing. F prime of a is the limit of h going to 0, absolute value divided by h. And now we have the opposite simplification, so a is negative, absolute value of a is minus a, and also a plus h is negative for h small enough. So absolute value of a plus h is minus a plus h. And so the limit then gets you minus a plus h minus a divided by h. This simplifies to limit of minus h divided by h, and we get that the limit becomes minus 1. And then the last case, a equal to 0, we get f prime 0 equal to limit h going to 0, absolute value of h minus absolute value of 0 divided by h. Absolute value of 0, of course, is 0 itself, and so we get this expression. Now you have to be a bit careful, so let's look at both the left and the right limit in turn. So h going to 0 from the negative side of h, absolute value over h is, so here h is negative, so we get the limit of minus h divided by h, and we get minus 1. Whereas for the limit h going to 0 from the positive side, we get that this is limit of h over h is plus 1. So in particular, we see that these two things are not equal. So the limit overall does not exist. And the reason why you get these answers, you can easily see from a figure. So here, if we draw y equal to absolute value of x, so it's two straight lines, one going down, one going up. So you see here we have slope plus 1, here we have slope minus 1, and then in the origin, slope does not exist.